afternoon. This is my presentation is all about mathematical foundation for cryptography. Modern cryptographic system, particularly public key system based on asymmetric cryptographic algorithms, rely heavily on certain topics from the field of discrete mathematics that allow us to design problems that are efficiently solved if you have small amount of critical information, but astronomically difficult to solve if you don't. The purpose of this study is to provide you with efficiency grounding in integer and modular arithmetic so that you can understand and work with this algorithm. The main the main topics we'll be covering include basic notation of divisibility in prime numbers, as well as what the greatest common divisor is and how to find it using the Euclidean algorithm. We'll see that while division is not defined in modular arithmetic, and also we will discuss about the multiplicative inverse. Mm, and first, we discuss the greatest common divisor and how to find it using the Euclidean algorithm. Let's divide into outcome first. Upon the completion of decision, the learner will be able to have only one outcome, which is are going to understand the Euclid's algorithm to find the greatest common divisor of two numbers. So it's very clear that we are going to focus on Euclid algorithm, which is also called Euclidean algorithm. While we are focusing on this algorithm is for computing the greatest common divisor, simply GCD. The greatest common divisor is also known as the highest common factor or HCF. So whatsoever, the concept is the same whether you refer it with the name GCD or HCF. We are going to find the biggest number, the biggest divisor of the common divisor. If things are not clear, so no worries. Let's understand the operation of GCD first. So we are an example for understanding the GCD, the greatest common divisor. As already mentioned, we are going to find the GCD of two different numbers. That's why I have taken two different columns. Firstly, I'm going to take two different numbers. Let's say the first number is 12 and the second number is 33. I'm going to find the GCD of 12 and 33. How to find this? I'm gonna find the divisor and the common divisor and also the greatest common divisor. Let's first focus on the number 12. What are the divisor of number 12? The divisor of 12 are 1, 2, 3, 4, and 12. When 12 is divided by this number, we will get the remainder as a 0. And that's why we call this number as a divisor. So 12 has 6 divisor. And what are all the divisors for the number 13? The number 13 has a divisor 1, 3, 11, 33. So when 33 is divided by this number, we will getting the remainder is 0. So we have complete finding the divisor, and let's now focus on the common divisor. Now in this set of divisor, what we are or common divisor we where we have on one here, and also we have one here, and also there have three. So we have complete finding the divisor. So let's now focus on the common divisor. Now, in this set of divisor, what are all the common divisor here? Mm, we have one here, and also we have one here, and also we have a number two in this set here, and also in this set is there have no two, and back to this set we have three, and this set is three. Hindi natutulog. Mm, is there any other common divisor there? So no, we have common divisor as a 1 and 3. So the common divisor is 1 and 3. And now we are going to focus the greatest common divisor. There are two numbers, 1 and 3. Which is the biggest number? Which is the greatest number? The greatest number is 3. So the greatest common divisor is 3. Let's move the question. Find the GCD of 12, 33. If you note here, these two numbers are not prime numbers, right? If these two numbers are prime numbers and these two are different numbers, they can easily say that the GCD is 1. But in this case, the two numbers are not prime numbers. So in this case, we are going to use Euclidean algorithm or Euclid algorithm for finding the greatest common divisor. So we are so what we are going to do, just create four column like this. Like this. The first one is the quotient, and the second one is two parameter A and B. Because we are going to compute GCD, we are going to compute the GCD of two different numbers. So 12 and 33, we have two numbers here. So we are going to take A and B as a two variables. And obviously we are going to do the division. Division has two outputs. Right one is the quotient and the other one is the remainder. So the first one is the quotient and the second one is R is the remainder. So just take four parameters like this in four columns. Quotient, A and B, and remainder. Now we are going to take these two numbers, 12 and 33, which is the biggest number in these two numbers. So this 33, right? Always use the biggest number in A and the next number in B. In this example, we have 33 as the biggest number. So 33 in B. So A also 33 in A and B is 12. So let's do that now. Here 33 and the 12 is in B. So I'm taking the biggest number 33 in B. I already placed here. Now do the division operation, and whenever you find find the b becomes 0, then whatever is then there in A, that is the GCD. I repeat, do the division operation whenever you find the A parameter with 0 as the value, then whatever is there in A, that is the GCD. No worries, things will be clear, and we'll see this example. So let's do the division operation. Do A mod B, A mod B, you're going to do like this. You're going to divide A mod B. You are going to do the operation A mod B. This is divided by B, right? So 33 mod 12. So when you divide 33 by 12, 12 times 12 and 2 times 24, and the remainder is 9. We have the quotient test 2, and we have the remainder as 9. So clear that the quotient is 2 and the remainder is 9. So we're first now is over are getting B as a 0 here. So there we have, so there's no 0, and we have to repeat the operation. And just see here, let this B go to this place as is B is in put into A now, and the remainder is B now. Now just shift the value. So when you shift the value, 12 will be in A, in B, the value of B will be in A, and shift the value 9 into B. Now carry out the same division operation again. 12 divided by 9, 9, 1 times 9, and the remainder is 3. So 1 is the quotient, and 3 is the remainder. So we know that we will get here. So 1 quotient and the remainder is 3. So we getting B as a 0? So there is no 0 here. And the things we do is so there is no 0. So we are going to repeat again the operation. So 9 is already, so 9 is going to replace here in A, and 3 in the B. So now do the operation again. 9 is divided by 3, and 3 times 9, and the remainder is 0. So 3 is the quotient, and the 0 is the remainder. So we get the quotient as a 3, and the remainder is 0. And now we are going to stop to this. Also no, because I told you, whenever your B is 0, then the A is the GCD. Is the value, is the B, 0, is the B has a value 0 here? No, so it is still. So do the shifting operation one more time. 3 as A and 0 as dB. Right now, perform the same division operation. So we're going to divide 3 by 0. So divided by 0 can't be performed. No, so need to stop. Mathematically is not valid. So number cannot be divided by 0. And obviously we cannot get the quotient and the remainder. So right now, see, we have the 0 in B. I told you whenever there is A in A, number 0 in B, then whenever is in A is the GCD. So what is there in A? It's 3, right? So the GCD of 12, 33 is 3. So it means 3 is the biggest number that can divide both 12 and 33. Then we will proceed to the next topic, which is the modular arithmetic. Modular arithmetic, which is sometimes called as the clock arithmetic, is a system of arithmetic for integers where the numbers wrap around after they each a certain value, which is called as the modulus. Let us use a clock for the example and replace 12 by 0 starting from midnight. The hour had point in order the following: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 0. And as it reaches noontime, the 4 hand points on the same order, and this is the way in which we count in modulo 12. Think of the modular arithmetic as that of the remainder in division, because the operation in finding remainder is sometimes referred as the modulo operation. Suppose we divide an integer by 5, of course it will we have remainder 0, 1, 2, 2, 3, or 4. If we divide an integer by 7, it will we have 1, 2, 3, 4, 5, or 6 has the remainder. If we divide an integer by 10, it will have 0 to 9 as the remainder. Thus, we define z sub n, or an integer z divided by n, as the set of integers from 0 to minus 1 modulo n. So we have z sub 3 equal to the set of integers 0, 1, 2 modulo 3. Z sub 5 is equal to set of integer 0, 1, 2, 3, 4 modulo 5. Z sub 8 has set of integers 0, 1, 2, 3, 4, 5, 6, 7 modulo 8. Note that Z sub n has n non-negative integer, which are basically integer from 0 to minus 1. Consider that in Z sub n, modulo is simply remainder when integer is divided by n. That is if you divide b by 9, it will be have remainder which is less than n. Since of course the value of a will be from 0 to minus 1. We will written as a is equal to b modulo n. Note the parenthesis may or may not be written. If we were asked if we were asked to find 4 plus 9 in z sub 8, or in other words, we are divided by 8, what is the remainder of 4 plus 9, or 13? And that is 5 is the remainder when 13 is divided by 8. So we write 5 is equal to 13 modulo 8. In z sub 8, what is 15 plus 21? That is 4, since plus 21 or 36 when divided by 8, giving us a remainder of 4. So may write 4 is equal to 8 to 36 modulo 8. Ano ko na siya? In z sub 15, meaning if we are going to divide by 15, what is 11 plus 12? That is 8. It's because 8 is a remainder when we divide 23 by 15. So may we write 8 is equal to 23 modulo 15. How about 106 plus 102 in z sub 10? That is 8. It because 8 is the remainder when 208 or 106 plus 102 is divided by 10. So may we write 8 is equal to 208 modulo 10. In z sub 9, what is 22 minus 3? The answer is 1. It because 1 is the remainder when 19 is divided by 9. Or in other words, when you keep on subtracting 9 from 19, and as you reach the numbers of 0 to 8, you will reach the number 1. So may we write 1 is equal to 19 modulo 9. How about z sub 5? What is 3 minus 20? The answer is 3. You may keep on going to adding 5 with negative 17, and as you reach the number from 0 to 4, you will get 3. So may write 3 is equal to negative 17 modulo 5. 11 times 5 when divided by remainder is 3. So we may write 3 is equal to 55 modulo 14, modulo 4. In z sub 11, what is 9 times 10? The answer is 2. It because 2 is the remainder, 90 is divided by 11, or in other words, subtracting 11 continuously from 90, and as you reach the number from 0 to 10, you will reach the number 2. And now we are done into modular arithmetic, and we will proceed now to the multiplicative inverse. So, multiplicative inverse is defined as the reciprocal of a given number. It is used to simplify mathematical expression that the word inverse implies something opposite, contrary in each other position or direction. A number when multiplied to each multiplicative inverse result in 1. So let us have the multiplicative inverse. So when we say multiplicative inverse, so let us recall the multiplicative inverse in algebra. So the product of two numbers. So meaning, for example, we have the product of 2 and 1 and a half, 2 and 1 and a half. So if the product of this number is if equal to 1, then we can say these two numbers are multiplicative inverse of each other. The other are the multiplicative inverse of each other. So meaning 2 is inverse of 1 half and 1 half is the inverse of 2. And the same concept, if we have applying the modular arithmetic, so ganun din. So since is the equal 1, so yung ang ating nagiging reminder katulad ng sa additive inverse. So this is a given congruent. So we have the product congruent to one modulo. The modulo is depende sa mismong given. For example, so we need to find the multiplicative inverse in of 2 in modulus 7 arithmetic. Ibig sabihin, ang hahanapin natin is inverse ng 2 yung naka-multiply dun sa 2 congruent to 1 modulo 7. So the value of n or modulo 7. So i-translate natin. So we have given 2 times 2x congruent to 1 modulo 7. This example. So, ito yung value ng x, yung hahanapin natin ng inverse ng 2. And then, when you divide yung nandito by the modulus, it will be equal to 1. Para masabi natin na that is multiplicative inverse of 2. So, iti-test natin ang mga possible value of x and madali naman hanapin ang possible value of x. It must be from 0 to n minus 1. So, ang n natin is 7 hanggang 6 lang. So, i-test natin isa-isa. If x is equal to 0, if x is equal to 0, ito yung magiging 0 niya. Yung this one. So 7 is over, also 0 is over 7. So remainder is 0. So hindi yung x is equal to 0. So that's not the inverse. The next, x is equal to 1. So yung magiging value natin dito magiging value natin dito is magiging value ng a is 2/7. We cannot divide 2 by 7, so meaning dito yung remainder. Hindi ito yung remainder. So, yan. So, next is 2 times 2 is 4. So, 4/7. So, hindi rin magiging remainder ang 1. So, next, hindi ko nauna mo dito. So, next, 2 times 3. So, 6/7. We cannot divide 6 by 7. Magdidesimal lang yan. So, next, we cannot divide 6 by 7 kasi magdidesimal lang yan. And the last is 2 times 4. So, 8/7. So, when you divide 8 by 7, the remainder is 1. So, dito natin nakuha yung sagot. So, dito natin nakuha yung sagot. So, dito nag-satisfy. Ibig sabihin, pag nag-satisfy dito, the multiplicative inverse of 2 is 4. Then, multiplicative inverse of 4 is 2. So, ganun. So, check na siya. The multiplicative inverse of 2 is 4 and the multiplicative inverse of 4 is 2. And that's all. Thank you.